Okay, so I picked this talk. So this is the PhD thesis of Nasgal, who's sitting here. So she will be answering many of the questions, hopefully. So the first one is applied to healthcare, and the two others are extensions that we started working on afterwards. So the first paper is a talk on physician scheduling using metaheuristics in a setting where we have uncertainty. And so we did this when she was still a master's student, and this was, it's a published work. And a few years later, she came back to do a PhD, and then we have this project, the Learning Taboo Search, in collaboration with Nadia Lahrichi, and the third paper I'm going to discuss is with Sébastien Digabel on blackbox optimization. So all people from the Magie at Polytechnique. I also picked these three because the first one is finished, the second one is under review, the third one we're still working on. So I think it's always nice to have a little bit of a finished work, still we're thinking about it, how it's going, and so on. So they can stop me if they have questions, right? But we don't need to wait till the end. Do I have a pointer?
Yeah, what you want? I guess should be
this one.
Yes.
Okay. Okay. First paper. So this work has been done with the Centre Intégré de Cancérologie de Laval for a radiotherapy treatment. It's a center that actually provides many services, but I'm just focusing on the radiotherapy one. So what's patient flow? Just to give you a little bit of background, in this paper, what's interesting is that when you're looking at the patient journey, it's not, so you have the very simple one where you go see your physician, you go see your GP, you get there, you see the physician, and then you're gone. So the flow is very, very small, and there is nothing much to optimize except from the booking appointment. In this problem, there are many things. So in the patient flow, you have multiple activities, you have multiple resources that you want to be meeting with. And the idea of optimizing the flow is you want to streamline this flow because you want it to be as smooth as possible. So what are the challenges? So usually you have different resources, being people or being different machines. You could have appointments or people to see on different days. So then it becomes a multi-day optimization in the flow. You have variability in demand because usually you do not know exactly when people are coming. You also have variability in the number of people, when the people are coming, and what type of people are coming. So you have all this uncertainty to handle. And the bottlenecks are usually the different resources. So the machines in this case, or the staff. So this is a very large background on the patient flow if you want to optimize it. So in a radiotherapy center, what happens is, a little bit of story. So the patient arrives. So with this, I do not mean the physical arrival of the patient to the clinic. It's actually a request that's going to be sent to the radiotherapy center that's going to trigger the patient flow. And then you start. So usually it's a request for a consult, and then you're giving an appointment for a consult. Then once this is done, you would be taking a scan. I'm going to say you, but I don't mean you. You're going to be taking the scan. This does not need to be done on the same day, obviously. Then you have a complete step that we call the pre-treatment, where things are happening with the results. So basically what's happening is the physician will be doing the contour, and then someone will be calculating the doses of radiations. And then we would be doing some validation and then preparing the treatment plan, and then the treatment can start. So if I was working on the booking part, then it would be working on this date here. So we have done that on a different paper. But on this one, what we're looking at is when we started looking at this problem, we realized that it's actually the physician here that needs to do many things. And all these tasks are not done on the same day. So if they're not scheduled correctly, then you do have some delays occurring. So clearly, the physicians were a bottleneck here. So if you're interested by this, there are many works on streamlining the radiotherapy centers, doing some simulation to smoothen the flows and all that. So on this one, it's really on the scheduling part. So we decided that we would be working on this problem here. What happens? Yeah. So what's the objective? So my objective is to find a weekly schedule. Why a weekly schedule? Well, because they work with weekly schedules, as simple as this. But also, since there is a lot of repetition on how the schedules are, the idea is have something that's cyclic. It's based on a 1 week horizon, and we have two objectives. The first one is to shorten this pre-treatment phase, which is what I just showed you here. So in general, if you count exactly how much time this would take, it could be 4 days in the minimum. But then in reality, it was about 5 to 7 days. So the idea is to have this as short as possible. You obviously have some wait time between two tasks because it requires time to do the calculations and so on. So what we want to do is to shorten this phase. And if you have ever done scheduling in the healthcare system, then you have to make sure that we're maximizing the preferences of the physicians. So the physicians are actually, so they have the tasks in the radiotherapy center, but they may have something else. But I mean by something else is doing other clinics, having conferences, maybe teaching, and so on. So the schedule, you need to account for all these this constraints. And then the idea is, well, since we do not know when the patients are arriving, how many are arriving, and what type of patients would be arriving, then we wanted to consider two types of uncertainties. The arrival of the patient, so how many on each day, and the profile of patients. So we have two items on the profile. One is, are these palliative or curative patients? So usually curative patients is a patient that you want to cure. So you do have some time to start the treatment. And the palliative patients, well, there's no cure anymore, but what you want to do is to reduce the pain. So sometimes they may just even skip the scan and just treat the patient on the day off, because that's what is the most important. And the second thing is the type of tumor, because every physician is a specialist. So you would have the gynecology, oncologist, and then you would have the, I don't know, the ENT, and then you have something else. And the idea was from day one that we knew that we were going to need a heuristic to solve the problem, because at the time we thought that maybe we could give them the prototype for them to use. So we did not want to use like any type of a sequence or anything like that, or license. So what does it look like, a schedule? So let's have just one very simple example where I have 4 physicians and then my week. In the first example, we only have one block, meaning one task. And on the second one, we have 2 tasks per day. So usually in the healthcare system, we work very often with the 2 tasks per day. In this center, they work with the 2 tasks per day. It's really morning and afternoon because there are shift changes sometimes after lunch and so on. And the idea is to determine when each step, when each task should be scheduled. The idea is I have physician 1 with one type of specialty. This person does task A, and task A is the consult. So everyone who's coming on the Monday would be seeing physician A, basically, if I'm assigning A. So you could wonder, but why do they have this task start? So what happened in different centers is when it's not task schedule, people tend to not do what they're supposed to be doing. So they don't like the contour, for example, so they just leave it. And then, well, then you have delays, and it doesn't work for the treatment to start exactly on time. So in this center, from day one, they knew that best practice, everyone should be scheduled, so then basically every task can be done at the right time, let's say. And what was very interesting for the rest of the flow is that if they knew that physician C is going to come, that physician 1 is going to come to do task C, so the dosimetrist would do everything to prepare all the files for the doctor when he would arrive. So it actually scheduled all the tasks in the center. So scheduling the physician, has also an impact on the entire flow of the files. Okay, so I'm not going to go really through the model. I'm just going to highlight few pieces. So it's a task-based model. So we have solved the pattern-based model just to do some comparison, but I'm just showing this one. So you have a number of physicians, you have a number of patients, you have two sets of profile. Once again, what's important is just that for one, you can skip tasks and go very quickly, and for the other one, you really have to plan on the tasks. And then we have the tasks ABCD. We have more than that, but let's call them ABCD for now. We have a 1 week, and then if you want to solve a 1 week problem, then the problem is that you have to consider actually 3 weeks, if I'm not mistaken, just because if somebody arrives on the Friday, then you need time to process everything. So just to have the complete horizon. And then what's in blue is whatever will become stochastic at some point. So in the deterministic case, I know when the patients are arriving, and I know what is the profile of the patient, and I know what's the tumor type. You have a minimum number of days between tasks, and then you have the preferences. And so you could say, well, so what's the challenge if a physician A is doing all the consults on the Monday, so given that that person has the right skills? The problem is they have this idea of quotas where everyone has a maximum number of new patients they can take every day and a total number that they can take in every week. So you have to balance when everyone is doing the consults. So where you see consults is obviously not only for the new patients, it's also for all the follow-ups. So some of the new patients would go on the A, but you can have many A's because you can have all the rest of consultations to happen. My variables, I'm not going to show my variables because I can relate them later to the moves in the tabu search. So one of the questions is physician I, which task this physician is performing on each day? So it's either on a day or on a slot. And if one patient is assigned to a physician, and from this you have the auxiliary variable that will tell you which task is each patient actually doing on each day. My objective function, as I said, I have the two components. I have to maximize the preferences. So I have a score for each task on each day for each physician. And I have the patient part where we're looking at to minimize the difference between the pretreatment duration and the first day and the arrival. What's after? Yeah. So in this version, I don't have the weights in front of the objective function, but you can imagine this with the weights and like only considering one piece or the other. So we have done these experiments, obviously. And then you have the usual constraints. So you have the blocks for the capacity constraints. Each task needs to be done once. And then you have the block of constraint to make sure that the schedule is cyclic. So I'm using 3 weeks to make sure that everything is repeated correctly. Okay. So to solve this, we obviously use Tplex. No problem with Tplex. It does solve. It gives you a result. And then we started looking at the tabu search method that we were going to use. So what's tabu search? Very briefly, because I guess everyone knows. So you start from an initial solution, possibly infeasible. Then you have to apply some moves that we need to choose. And then you have to, you're guided somehow inside the solution space. And then you end up with one solution in the neighborhood. The solution in the neighborhood is usually the best non-taboo solution. So you have an objective function here that you need to consider. To get to the neighbor, you have a move that you have to determine. And then you have a taboo list that actually prevents you from going back to the previous solution, where usually, well, so you can just imagine you are at the best solution and then you move to the neighbor one, and obviously the neighbor one is not as good as the one that you had before. If you just say go to the best solution, it would obviously come back to the solution where it was. So this cycling is, this taboo list is preventing you from doing that. So what are the moves? So actually, if you look at the problem, you have two problems. You have the first one, which is the scheduling part. So which task I'm giving to which physician. And then you have to do the assignment of the patients. So on the variables, I showed you one variable, like the two variables had this complete information and the two problems were integrated. So if you look at the schedule of the physicians, then you have the first one, which is the easiest one. So you have this task, 1, 2, 3, 4, and one is repeated for another reason. I'll explain in a second. So the first move is very simple. You just swap two tasks in a given day for all the physicians. So in this one, you swap 1 and 3, 1 and 2, 4 and 1, 2 and 3, and so on. You pick the best. And let's say that the best is swapping 2 and 1 for physician number 3. So this is my first move. Yes?
Yeah, when you swap two tasks, should you complete the new solution each time? Or do you have some way to predict the new, maybe the new objective function?
So we don't predict. In here, we like it's a straight normal taboo search with no machine learning. I just calculate the objective function and I get the solution. Yeah. And then the second one is to change the repeated task. And the reason why we have these repeated tasks is very simply because we have 5 days, 4 tasks. So one of them is going to be repeated. So you just need to change which one. So for example, in this one, we had T1 being repeated. So you could change it to T2, T3, or T4. In this one, it's T3 that was repeated. So you could change to another one. And let's say that in this one, you pick T4 to be repeated on day 1. So basically, these are the two moves that will make sure that whatever you do on the, if you go from one schedule, you can end up with every possible schedule. So you're sure that your solution space is going to be completely visited if that's what you want to do. And then you have the assignment of the patients. And for this one, well, it's straightforward. Then you have patient 1 that's assigned to one physician. You need to change the physician assignment to another one. And with these 3 moves, you have pretty much changed all the, if you look at your variables, to move everyone from 0 to 1, this is exactly what the moves are doing. So the complete procedure, you start with an initial solution, you calculate the cost, you have move 1, and then with move 1, you calculate the cost. Is it improving? Yes or no? If it's improving, then is it taboo? And is it better? If it's better, then you have to update the best solution. If it's not better, then that's fine. So you can keep going. And then if it was not improving, that's fine as well, because in taboo search, you allow for non-improving solutions to be visited as a neighbor. And then you keep going. Then you go to the following moves. So after some iterations, so we do count the number of iterations. After some iterations, then we start changing the moves. We have 2 types of moves. We have the move 2 and then move 3. And for each of them, we have a rule on when we would pick one move or the other. And then we have a number of iterations for each of these moves. I'm specifying these because all these are my parameters in my taboo search. My parameters are, I started with move 1, and then I do move 3, and then I do move 2. I could have done something else. So we did experiment, but sometimes when you do the parameter tuning, paper 3, then you could go back and then you could say, okay, so should we revisit the way that we have done that? And this is the idea of the 3rd paper. So if I don't get to the end, this was the plan. So many experiments, we kept the best. What I'm showing you here is what was the best at the time when we did the work. And then you have the uncertainty part. So in the model that I showed and I shared, and the taboo search I shared, it's a deterministic version. I know when people are arriving. I know what is their profile. and then I schedule everyone given that information. Now, I don't know when people are coming, and I don't know what's their profile, but I still want to have one schedule that fits every single week. So I want the same schedule over the year, but every week I may have different arrivals with different profiles. So the objective is to have one schedule that's going to be the best. And then, like, obviously, you would have questions. So how am I going to be comparing my solutions? And what's the best solution? So obviously, I'm not going to be solving the schedule every week given the arrival pattern, because the idea is to have the same schedule for the whole year. So just like maybe a refresher and where we got the idea from. So usually when you do deterministic optimization, you have this objective function. And then when you do stochastic optimization, in one of the methods that uses this sample average approximation, you minimize a function f, and then you consider all these scenarios. In my case, it's all my scenarios of arrivals of the patients. And I do have some function here. And I'm considering all these scenarios in the second part. So we use this idea to say, well, then maybe in the way I'm calculating the cost of a move, instead of calculating the cost of the move on one pattern, then we should be calculating the cost of the move as an average on all these scenarios. And this is where this part here is applied. So the cost of one move now is, I'm going to change the assignment. So I change the assignment and I calculate the cost. But then it's better with the task. So instead of doing consult, you're going to do contour. I just do that. But then given all my future scenarios of arrivals, then the cost could be very good with one pattern, very bad in one pattern, and so on. So I pick the one that is the best on average. You could say, but maybe you should have used the max, the worst, the 90%. I could have changed the measure. We use the average because that's what we used. I mean, we wrote the paper, so we got to choose, right? Okay, so what's the, yeah?
Just now, the scenarios. So how do you get all the scenarios? Like,
yes.
This is the team about that.
So I will get back to the scenarios in 3-4 slides. If I don't say anything, just raise your hand again. Okay. So how is it going to work? So this is exactly what I had before with my tabu search. The only difference now is that when I'm picking a neighbor, X prime, this time I'm not picking with the best Fx prime in the neighborhood. I'm picking the one that's going to be the best on average on all scenarios. And then that's it. And then I pick that one. But then what happens is also that one of the moves, which was the move that was using the patient assignment, is not anymore something that can be used in the same loop, because I solved the scheduling part, and then the assignment, it depends on the patterns. So on each iteration, what do I do? I pick a task, for example, because I'm changing, like let's say I'm doing either I'm changing the repeated task or I'm swapping 2 tasks. So I do one, and then I look on average with all the patterns, the patient arrivals patterns, what's going to happen. To determine what's going to happen with each patient arrival, I need to solve the patient assignment. So within each iteration, I have to solve another optimization problem, pick the best assignment, and then I have the solution. So it's, yeah. And then I update the tabu list, and then we're done. So this is how we went from the deterministic tabu search to what we call the stochastic tabu search. So some results. So obviously we have 2 sets, the created set. So we created 18 instances with different sizes of a number of physicians and number of patients. So here, what's going to be interesting, and so I confess that the classification, we did not have it when we started the paper. So we thought that it will be big if we have a big number of physicians, because that's what we were scheduling, right? But then we realized that it's the ratio between the number of physicians and the number of patients that make the problem difficult. So sometimes you don't know when you start, but then you know at the end. Well, I just show you as if we knew. And then we have the real data from the partner, but I don't think I'm showing you the results on those. So just to show you
for the partner organization, what is the average ratio between the patients and doctors?
I don't remember.
Okay.
What was the ratio? The real size of the instance, what was it?
Oh, it's fine. It's fine. It's fine.
It was her master's. Yeah. Be nice.
Okay. Yeah.
Okay, so some results on the deterministic case. So this is just to show that we obviously all know that having two tasks is better than to have one task in a day, because then you have more flexibility. But just because we were doing the work with them, we wanted to show that quantitatively what they were doing was the best. So these are the pre-treatment durations for the curative patients, and these are for the palliative patients. And as you can see, it's obviously shorter for the palliative patients because you want to speed up the process. We did some variations in the objective function. And obviously, if you look at this here, if you do not consider the physician preference at all completely, then there's no variability at all on the pre-treatment time. And everybody can be done in exactly 5 days, and everybody can be done here in 3 days, and that would be it. But it's a non-feasible, realistic solution. Okay, and then for the stochastic version, which was what we wanted to solve, actually, so the idea is we wanted to generate a stable schedule. So the procedure to generate this schedule is that we generated 2 sets of instances. The first set to build a schedule, and the second set to test the schedule. So with the first set, you generate a number of scenarios, 10, 30, 50. Well, 10, 20, 30, 40, and 50, because we were really testing. And so to your comment, we use the data from the CICN to have some information, and that's what we use to generate the patterns. So what does it mean, the patterns, these scenarios? So what does it mean to have 50 scenarios? So 50 scenarios means that I have 50 weeks worth of data, because for every week, I would know when the patients would be arriving, like what day, with what type, and what's the tumor type. So if you had 1 year of data, then you're basically using 52 scenarios, so it's very close, about 30 or somewhere within 6 months. So this was the idea here. And then once we have this schedule, which is supposed to be the best solution, then we generated another set of scenarios, and we just tested the schedule obtained, our best schedule obtained, to see how good it is or not after that. So you have many experiments. So the first one is to determine, do I need 10, 20, 30, 50? Because that's important in order to know like how much information you should know to have something that's stable. If you know, like if 6 months is enough to know about your center, then that's enough to generate a schedule, right? Okay, so on here, what we have are the solutions. So L1 is the deterministic, and then you have all these stochastic values on here. We compare the averages. We also compare the standard deviation. Seems that 30, so if you look here, then you have 20 and 30, same average, very similar standard deviation. So basically, if you have 30 scenarios, then that's good enough. You don't need to get to the 50 scenarios to get your solution. So that's what we kept for the experimentation. So that work was done. That work was finished. We presented the schedule. It was interesting. So what we did also is that we took their schedule and we tested it with our instances. to have a comparison. And then we took our schedule and we tested it with their real instances. Basically, the gain was 1 day on average. So it's 1 day times more than 1,000 patients a year, which is 1,000 days, right? So you would think it's good. But so since it was only 1 day, it was not worth changing the complete schedule at the center and have everyone be moving around. So we did not implement. So we kept our C++ code with us, and it's still with us, which is good. It's fine. So then a few years later, with all the development in machine learning and so on, we revisited the problem and we had many questions. So if you look at one iteration in tabu search, what happens? You go from the solution, you take your move, and you generate all possible neighbors. And then you pick the best, and then you go again to the next solution, and then you redo the same thing. So the amount of information that you're generating within 10,000 iteration is huge, and we're not using that information. So we do use some information, which is the frequency of the move. So we do have few things. We have diversification and so on. But then the idea was, is there a way that this information could be leveraged to do better? What we thought would be better is to get a better solution quicker. So let's see what happens. Learning tabu search. Is there a way to improve? And we didn't know. So what type of methods? And how do you actually measure the improvement? It's a real question. How do you know that it worked? So what type of methods? I'm only showing the ones that we actually kept at the end, but we did many, many things. Well, she did many things. Started with the Q learning. We did many things. The problem was that it was slow. So everything was super slow. And that was the main, and it's the main challenge actually in this project. So having this meta-heuristic being combined with something else to improve the performance obviously was not new. So there is a survey, 2011, that shows that like basically the families of combinations with meta-heuristics are two or more meta-heuristics, obviously math heuristics, or this new learning methods. So with the learning methods, what was done? Oh, yeah. So let me skip one and then I'll go back. So what type of learning approaches were used? So you have different things that were done. First one is to use learning to better select the right algorithm. You have to, so learning generative models of solutions, whatever that means, you ask her. Learning evaluation functions. So to your questions, do I need to calculate the function or can I just predict it? So this is some sort of work that's been done also, but we're here in the search space. So our idea here is really, well, since I have this huge space and I have a lot of information, is there a way that I can be guided better with the learning algorithm? And I'm not going to say proof, but there is evidence that having a little bit of machine learning in the search space is supposed to be good. So in this research, I'm going back, the idea is really to enhance the search procedure. That's the plan. Learn information from the search space to better choose a neighbor. That's the plan. So instead of evaluating all the neighbors and then pick the best, the idea is that can I just reduce this choice, and instead of evaluating all the neighbors and just picking one, can I reduce that size? And we kept classification methods, but as I said, she has tested many. Quick refresher, 3 moves. I have this one, the second one, the third one. She tried to learn from all of them, but basically the first one is the one that we could learn from. It's the one that generates a lot of information. It's also because it's the one that's used the most. If you look at the taboo search procedure that we have, it's our real basic move. It's also our basic move because in the experimentation that we have done before, we realized that it was the one that had the biggest impact on the search procedure and on the improvements. So it's one of the reasons. So why learning? And then you have multiple questions because then you can, I mean, there's different ways of looking at the problem. But what we know, we want to extract some useful knowledge. This move is no good, don't do it. This move is promising, do it, and so on. We want a guide, and we were hoping to have a better exploration of the search space. Well, we're still hoping that we have a better exploration of the search space. The problem is, if I can say the problem, is that you don't know exactly how better you have explored because you've explored differently. How do you measure better? So unless you improved, but even if you did not improve, can you say that you have explored better? It's not clear. So I don't have the answer to this question yet. So then you have all these questions. So what do you learn? So what do you want to learn? Do you want to predict the complete move? Or do you want to just reduce the space? It's an open question. What do you consider to learn? So what's the information that you need to learn from? Obviously, which method of learning? And if you want to start learning, so how do you do that? Because you obviously need to collect some information. So you have this collect information part. But how long should this part last to have enough information to do actually something with it? So all these questions are all parameters that are tested, and I'm gonna go quickly, let's say. So the main idea is that you reduce the space. You reduce the space in terms of at each iteration, when I wanna check, when I'm looking at my neighbors, I'm trying to do something better. So if you look at all possibilities, what does it mean? I have a number of, well, P, M, and K. So you have the tasks, you have the physicians, and you have the slots or days. So you have to try all the combinations. But then, so this, P times M times K, it's very big. And you wanted to, like, you want to reduce it to something, but the something, it really depends on what type of move you want to have, like what type of prediction. So if what you predict is exactly the move, then it's 2-1, because it says, do this task on that day for that physician, and then you're done. Or it could say, well, pick the day, and let's see. It's like, okay, I observed somewhere in my learning that day 4 was problematic. So let's try to see what's the best solution in day 4. So now you just divide it by K. Or you could say, let's pick physician number 3 and check what I should do with physician number 3 because his schedule or her schedule is not being good. So you actually can really decide on what you do. So we know it's awful. It's not good. We will redo it, but I will show it to you anyway. So you have 3 phases. You collect the information first, and then you do your training, and then you start doing your predictions. Like you really have these 3 phases. How do you do that? So we have the 2 versions, what we call online and what we call offline. What's the online learning? So these are all my instances, and I pick 1 instance at a time. So I'm solving the problem for 6 physicians and 40 patients. I pick this instance, I run my taboo search, I collect information, I train on that information, and then I start applying, I get my solution, I'm done. But then you could say, okay, but so you can remember that this is in the stochastic setting. Can I learn from an instance 660 but then apply whatever I find in an instance 640 or 660, but with a different arrival. Or, so can I use any instance to learn from and apply to a different instance? Yes or no? So this is the question in the online, offline. And we thought at the beginning that this figure showed this, but I guess it does not. Right? So this what it means is I use the complete set to do my collect, train, and apply. And I just do the apply for each instance individually. So is the learning instance specific, or can I do my prediction on a bigger state or a bigger number of instances? So what we used, logistic regression, decision trees. That's what we used. And we compared to random. To show if we learned something. Features, this was a lot of work. I think this was the biggest part. Because then you look at the solutions and then you go back and then you start understanding what happened, why it happened, so then you can give all the information. So we categorize this 4 categories. One that has to do with costs. And these are values. One is the value of delta x. So +3, -4, and so on. Am I improving, yes or no? So was this an improving move or was it not? Then we have information about taboo. Was the solution in the list? How long was the list? What's the frequency of something? A move, probably. And then we have the real solutions, the complete solutions. Because if you look only at the cost improvement and you say, oh yeah, but changing the task on Tuesday for physician 1 was improving, you cannot use this information as is because it depends what was the solution. Sometimes it's improving and sometimes it's not improving. So you have to have the solution. So we keep the current solution, but we also keep somehow the idea that we have a difference between the best solution and the solution we're at. And what's the neighbor solution? Well, like some information about the solution themselves. And so we need to have matrices stored. And then we have, yes.
Can I ask about that?
Of course.
If you want to learn across instances in the offline setting, how do you, I mean, the instances can be of different sizes.
Yeah.
How do you deal with that?
So how did you deal with the sizes of the instances in the matrices when you did the offline?
For example, I did a training on an instance with 6 positions, and I did the prediction of instances with 6 positions for different positions.
So we kept the size of the schedule. Okay, and then we have for the move itself, we have, and then for the move itself, we have also two different informations. So something that's, is it attractive or no? And then there is something, it's a paper by Thévenin and Zuffray that looks at the trail of the moves. So it's a sequence of moves that's also used. And then to evaluate if the method is good or not good. So we have what, like obviously you have the performance, and here we have the performance as just the cost. So is our learning algorithm able to reach the best solutions or not? And then you can look at somehow the time. If we do reach the best solution, are we doing better or no? We're not. And then is it scalable? So can we use this for small, medium, or not? And we have run a little sensitivity analysis just to show the impact of the features. So obviously, I'm just gonna go quickly, but we do have a design of experiments. We do have tested different values for each of the phases, the collect, the train, and the apply. Should it be static? Should it be problem size dependent? So if you see alpha, it just means that it's problem size dependent. And obviously it's going to be better. And then there are many other parameters that were tested for each of the methods, but I'm just going to skip this for now. Results. In terms of best solution. So when so in the meta-heuristic world, right, you compare two things. First one is the best solution reached, and then you compare on average. Because whenever you run something, you always run it 10 times, 20 times, 50 times, because depends on the seed you started from and so on. So if you want to know exactly the behavior of your meta-heuristic, you have to have like all these different ones. So here you have, do I reach the best solution? And on average, am I good or I'm not good? And it's basically what I showed also when I showed the taboo search. So if I look at the at the last line, what we're looking for is the smallest standard deviation and the smallest average. And there is one here that has so it's I3 alpha for training and I6 alpha for apply. So this means that bigger the instance, well, longer you have to train. Longer you have to train. And what we discovered is that the time to train, actually, it's the time to manipulate all the information and so on. So that's what takes time. So we basically have some implementation. The best implementations are using these ones, these parameters. And then we looked at the different feature sets in learning. So if you use them all, if you use only the cost, only the matrices, a combination of the current solution and the cost, just a few of them. And we could show that the best setting was the one where we have all the experimentation, all the features, sorry. But obviously we would have removed the ones that are not working. But okay. Now the time. So if you look at the time as is, you have the taboo search here. So how does it work in the taboo search? So what do you need to calculate at each iteration? Like basically it's plus and minus operations, right? So this is super quick to do. When you do the learning procedures, well, you do have the collect information, and then you have a lot of information that you have to handle, that you have to treat. So this requires time. And this is what we show here. So if you look at for each iteration in seconds, when the taboo search normal takes, I don't know, 20 seconds on average, we take about 27 seconds on average. So this is the online. And the offline is a little bit smaller because obviously you have done some learning before. So you don't need to do that. But then what we really use is the primal integral. So this, what it shows is, if I look at one example, like for example, this one, for instance, 6, 7, you have a compromise between the time and the value that you will be getting. So I'm going to show an example in a second. But what's important here is that for all the instances, so the green is not good, but the green is the random. So the idea with showing the random is that you can actually show if your algorithm is actually doing something that's not similar to just doing randomly, okay? So clearly we do see that we're doing something better. And blue is TS, and all our learning algorithms are the red and the yellow. So the red is sometimes better, and sometimes it's not better. So it's never better because of time, never. When it's better, it's because we could improve the solution. So the search was done differently, and we could find a better solution. If we look, so if you look at this part here, so here we're not good. On like when the instances are very big, we're not good here. But even when we're not good, and you look at the, I'm just gonna skip this, and you look at 2 instances. So here is one example, 820. So 820 is, where is it? 820 is here. So it is a similar. And I have 1040. And the 1040 was on the part where we were not good, okay? So what happens? So you see the blue is the TS. It goes super quickly, and then it has the best solution, and then that's it. If you look at the learning, it takes a little bit more time to get to the best solution, and then it improves the best solution, and then it stays at this best solution. So the primal integral value calculated was similar for this instance, even though we actually improved the best solution. But it's the way it's calculated. And then for this instance, the primal integral was very bad, as if we were not performing. But we did find the best solution. It's just that it took much more time. So the discussion and what I wanted to bring to your attention at the beginning were like, how do you know if it actually works or not? It's not that easy because sometimes it finds the best solution, but it requires more time. Sometimes it takes a little bit more time, but then it improves. Sometimes it's super quick. So it just depends. But overall, we're able to learn something and to find the best solutions. And then on the stochastic case, and it's too big, so the best is here and you don't see it. But basically, on the stochastic case, where we thought we would have the biggest impact, because obviously now you multiply everything by the number of scenarios. So if you multiply it by 10 or by 30 or by 50, well, here we do, you do have an improvement with the learning. So all these are a comparison to the TS, so to the normal taboo search. So here it's 30 scenario to 30 scenario, not compared to 10. So here we're not trying to set if 30 is better than 10 or if 50 is better than. We knew that 30 was the best. So are we even improving even more now that we have this learning procedure? And the answer is yes. In most cases, we're getting an improvement everywhere. So on all sizes of instances, we do have an improvement. We have the same information about the time and about the stochastic case. And here we observe the same thing, that sometimes we are very similar in the values. And if I show you an example, so these are the same two instances. You pick 820, where we were very similar and we improved a little bit. On this one, the taboo search is super bad. And here are the values. And if you look at the other instance, it does take more time for the learning to get to the best solution. So I'm only showing the orange line, but I could have shown you the green line, which is the decision tree. So the decision tree is much better than the logistic regression. I just picked the first line. Okay, last project. And I have
10 minutes. 5 minutes. 5 minutes.
Okay. Okay. So then, so this is a submitted. We're under revision.
Sorry.
It's what?
I was looking at other bodies.
Yeah, me too.
Yeah.
But let's skip.
That's 10 minutes.
Yeah, let's say this one is right. We can do that.
5 minutes. 5 minutes.
Okay, so 2 minutes just to give you an idea. So there is a group at Polytechnique that works with blackbox optimization. And what they do is many things to, like, for example, you have very complicated functions. Instead of calculating, what they do is they blackbox it. So what they do, the estimation of the value of f without calculating exactly the value of f. So like they have many different applications. And we started discussing with Sebastian, and then we thought, okay, like maybe we could use it for the hyperparameter tuning. The idea is that it is an optimization problem. I'm gonna go here. So how does it work? So this is Nomad. You give it a set of values of the parameters. And what you want to do is to find the best values of the parameters. So what are my parameters? The taboo list, the order in which I do my moves, and the number of iterations for each move. I have no idea how to do that. Like, let's say we did not know how to do that. And let's compare and see if it's good or not. So it takes this information, you give it to Nomad, and it tries different points. The way it tries the points is it picks a point. This goes in the black box. The black box is actually our taboo search procedure. It returns a value of f, and within Nomad, it does a VNS, it does many different things, and then it gives you another point to try. And then you try that one. And then at the end, what you get is the best set of parameters. This is Nomad. For some, you may have heard about iRace. So what we're trying to do is to compare with iRace now. So yeah. No, I'm finished. We have solutions, it works, and then final remarks. So the last two papers are really into her PhD. The idea is we know that in the metaheuristics, it's really on one problem. We could take that and maybe try it on different problems, maybe with other metaheuristics or so on. But the idea is that there is some work to be done if you combine with the metaheuristics. We know that there are some of the limitations. We know that training takes time. We know that learning takes time. We know it depends on the implementation. We have this problem as well. We know that it is also sensitive. For example, 1 year, it's sensitive to the parameters that you give. So the solution would depend. And I'm done. Thank you.